The next topic in our list of review topics, still in Unit 1, would be number 14, topic number 14, which would be static equilibrium. And static equilibrium and torque is a continuation of that last major topic in Unit 1. Now, if you've been following along these classes as we go, okay, all these little sessions one by one, you'll know that last time we talked about forces. And the most important concept that you needed to remember there was that when forces are exerted at an angle, it's a whole lot easier if we convert them into components. In other words, horizontal and vertical components. Because it's much easier to balance forces or work out net forces, etc., when they are balanced. In other words, when the forces are all either horizontal or vertical. So what we're going to do today, or in this session, is we're going to take a look at what happens when all the forces cancel out, because that's really what static equilibrium is all about, right? Static means not moving. Equilibrium means something is equal. So just the term static equilibrium should give you a pretty good idea what we're talking about. So the whole field of statics in physics and engineering is all about keeping objects motionless by applying forces. Like, in other words, if you want to keep a bridge up, you have to put supports there that are going to supply enough force to hold that bridge still, etc., etc. To keep a building from moving sideways, there has to be enough force there from elements of the foundation to keep that from happening, etc., etc. So statics, then, we can think of as the application of forces in order to balance other forces. So applying some forces to balance other ones. That's really all it is. Now, the other thing to keep in mind is that when objects are trying to be held in static equilibrium, there's really two kinds of movement that we're interested in. Okay, there's first of all translation, and you may have come across these in mathematics as well, but in translation, if an object is moving with a translative motion or a translation motion, that means the object is sliding from one place to another. Sliding along the ground or moving up or down or whatever. That's a translation. The other side of motion would be a rotational motion. And that one is pretty self-explanatory too. An object rotating in place or turning in place. Think about a seesaw, right? The two ends go up and down, but the seesaw doesn't actually go anywhere, right? It doesn't travel anywhere. It stays fixed. But it's still rotating around an axis. The hands on a clock, same thing. Hands on a watch, those types of things. So in order to maintain what we call static equilibrium, both of those types of forces need to be balanced. Both types. Okay? The translation forces and the rotational forces. Both have to be essentially equal to zero. The net has to be zero. That's in order to maintain a condition of what we call static equilibrium. Now, to get the idea of that, we need to talk about the idea of center of mass, or sometimes known as center of gravity. And all that means is any object has a point at which the mass almost seems to be concentrated. Okay, and if you think about your pencil, for example, there's a certain place you can hold your finger underneath your pencil so that your pencil would be perfectly balanced if you let it go. It would just stay there. That would be the center of mass of your pencil. Okay, now for uniform objects, that's usually right in the middle. Okay, so if you've got a pencil with no eraser on the end, pretty much exactly in the middle of that pencil will be the center of mass, because that's what we call a uniform object. It's the same shape, same size all the way through. Like the circle that you see there, like a sphere. Okay, this guy down here, that one has a center of gravity or a center of mass right in the very center. Whereas this one, you'll notice, is a little off-center. See the triangle? Okay, that means that in order to balance that triangle, on a single point, you'd have to put that single point about there. Because in other words, there's just as much mass on this side of the point as there is over here on this side of the point. Because it's actually thicker over here than it is over here. So all the objects that we are going to consider in physics, in this course at least, in Physics 3204, are going to be uniform objects. So as soon as you see the word uniform, that means that the center of mass is smack dab in the middle, right in the center of the object. And that's going to be important for the next topic that we talk about, which is torque. But I'm getting ahead of myself. Let's concentrate on just forces for now, the translation forces we're going to look at first. So in order to acquire static equilibrium, number one, we need to know what forces are acting on the object, the magnitudes of them, to make sure that they balance out. But it's actually equally important to know where the force is applied, because what we're going to do in this lesson is we're going to talk about when the X and the Y forces all balance out to give you 0. There will be no translatory motion. In other words, no translation, no sliding when that's the case. Like the cat here in the picture, 50 Newton force forward or 50 Newton force backward. They cancel out. No net force. We've also got Fy down, Fy up. That's the normal force up, force of gravity down. They cancel. In other words, that cat doesn't go anywhere. Not moving. Now, in this one here, we got a mother sitting on a seesaw with her son. Now, even though the forces are balanced out, they may move because it's possible that if the mother was heavier than her son, which is likely, she would push downwards. So the seesaw would actually rotate. So in order to prevent that from happening, the mother has to sit in the exact right position to not only balance the forces, but to be in just the right place so that no rotation occurs either, because that's equally as important. Now we're going to save that one for the next lesson, the torque. We're just going to look at the translation forces in this lesson. So let's take a look at how that works. So again, as we normally do, we're going to run through some actual examples from old public exams. Some examples from old publics. Examples, in this case, of problems that involve static equilibrium. So we'll start out with some definitions. And the first one is pretty easy. We just talked about that. At which point on a uniform object, can the force of gravity be considered to act? In other words, where does it appear the mass is concentrated? And of course, the answer to that is at the center of mass, or the center of gravity. Okay, they both mean the same thing. Then the second question there says, which condition will produce rotational equilibrium? Well, F net equals 0 doesn't do that, because that only tells us the forces balance. It doesn't say anything about where those forces are. So forces, that's not the key. It's the other one here, and you've done this course already, so you know that the rotational equilibrium is all about rotational forces, which have the other symbol there, not an F, but the Greek letter tau, which stands for torque. So in other words, the net torque must equal 0 to get rotational equilibrium. Okay, if F net equals 0, the X and the Y, that would be no translation. That's what we call a translational equilibrium. So there's a translational equilibrium and there's a rotational equilibrium. And then there's a static equilibrium, which is both of them put together. So in which situation would an object be in static equilibrium on the last question? And that, because of the word static, it would have to be motionless. In other words, not sliding and not rotating. Both of those are equally important for static equilibrium. And in other words, not only do all the forces have to cancel each other out, but they have to be in the right place so that there's no rotation either. Both of those things have to happen. In other words, there's two conditions that had to be met for static equilibrium. Let's have a look at this guy. We've got a traffic light suspended by two wires, and we want to know the tension in each wire. Now this is not too bad, because if you look carefully at the diagram, you'll notice that the two wires make exactly the same angle. But the angle that we're given, you'll notice, is measured from the vertical. Normally what we do is we use the horizontal angle. So the horizontal angle here is 12 degrees, and you'll see why now in just a second. In this particular question, if the traffic light is just hanging there, it's not moving, then we know that F net, the net force, has to equal 0. And that means that the forces upwards must equal the forces downwards. Well, the forces downwards is easy, because the only thing pulling down on that traffic light is gravity. So Fg is the down force. But the up force is the force provided by the tension in each of these wires. But the only thing is, if we're talking about the up force, okay, the up force, then I need to know what the vertical components are. So in other words, the force up, there's two tensions vertical. So two Ty's, because there's one on either side, one on the left, one on the right. But they both have the same magnitude, so I can put them together like that. I can say 2 Ty. So what happens is, Fg, remember, is mass, which is given as 35, times gravity, 9.80. And that happens to equal 343. So when I divide that by 2 to get Ty, I got Ty equals 343 divided by 2, which is 171.5 newtons. That's Ty. But that's not the answer, not yet. Because you also need to remember that Ty equals T sine theta. Okay, that's where the idea of components comes in. Okay, we got to use the Y component. But see, we're trying to find the actual tension in each wire. So we're trying to find T. In order to find T, what I have to do is this. I have to say Ty divided by sine theta. In other words, 171.5 divided by the sine of the angle. But remember, if I'm going to use sine for the vertical component, the angle that I'm using has to be measured from the horizontal. That's why I wrote in the 12s up there before. So 12 degrees. So I've got 171.5 divided by the sine of 12 degrees. And the answer to that is 824.9. That rounds off to C, 820 newtons. Now be careful here, because if you had gotten mixed up and used the 78 degrees instead of the 12, you would have gotten this answer right here. Okay, so you really got to watch it. You really got to watch that angle. If the angle is not measured from the horizontal, make it from the horizontal. That's the easiest way to do it. Okay, or you could just draw the triangle and use trigonometry to figure out which one to use. But it's usually a whole lot easier just to memorize the equation for this particular stuff and always use the horizontal angle. Okay? Moving on. Okay, similar types of questions. Which defines static equilibrium? Now we had one a minute ago for rotational, but static equilibrium, remember, is both. Not moving, in other words, F net has to be 0, and net torque has to be 0. Okay, because it's not rotating either. So that's met by the first one right here. If there's no net torque and no net force, that's static equilibrium. In other words, it's not moving and it's not rotating. That's the one. The single point at which the entire mass of a body is considered to be located, Again, center of mass, or sometimes called center of gravity. Just another way of stating it. Just another way of stating it. So all those things are definitions. Now, here's another one very similar to the traffic light one we did a minute ago, except this time you'll notice the two angles are not the same. So therefore, the two tensions are not the same either. And we want to know, what's the mass of this box? What is the mass of this box? And again, straight off an old public exam. Straight off an old public exam. I believe this one is off the June 2005 public. And for whatever reason, the June 2005 public is the only one of the past number of years which for some reason has no solutions posted for it. So we're going to run through the solutions of this one here right now. And again, if you're trying to find the mass of this box, you're going to find the force of gravity. So we're going to do it like this. We remember that F net in the y direction is equal to 0. Because remember, if it's just hanging there, that box can't go anywhere because the wires are holding it up. If it's not going anywhere, there's no net force. So F net y is 0. And that means that the forces up must equal the forces down. Okay, and the forces up are the two tensions, but the two y components of the tension. So what I'm going to call them is Ty, and there's one on the left, so I'm going to call it Tyl, and I'm going to call the other one Tyr, R for right. Add the two of those together, and they have to equal gravity, because that's the only force pulling downwards. So the way you do that, the tension in that wire is given. We know it's 427. And I need to convert it to a vertical component, so I'm going to say the sine of the angle, which is actually given as 62 degrees. And it is measured from the horizontal, you'll notice. So I can just go ahead and say sine of 62. Plus, I've got 270 on the right-hand side, times the sine of that angle, which is 42 degrees. And that has to equal mass times gravity. So what I've got is the left-hand side works out to be 557.7. And on the other side, I don't know the mass, but I do know that G is 9.80. So I just have to divide by 9.80, both sides. And that would cancel these two guys and leave me with a mass equal to 56.9 kilograms. And because 9.80, right, that's really 9.80, because of that, that's 3 sig figs. This has 3 sig figs, and this has 3 sig figs. Angles we're not usually overly concerned about for significant digit purposes. Technically you should, but that's not usually going to be the limiting factor for terms of significant digits. So I'm just going to leave this as 3 sig figs, 56.9. Normally, most of the angles you're going to see on the public exam are going to be decimal 0 for the most part, so that they won't be the limiting factor in terms of significant digits. All right, let's take a look at another one, very similar to the one we just did, only this time it's a little bit easier. It's the same type of question, but this time you notice the two tensions are exactly the same. The two angles are exactly the same. What that means is, instead of saying Ty left plus Ty right, we can just say 2Ty, because the both of them are the same. So we can just multiply by 2. And that's the way the solution to this one here is done. You'll notice forces up equal forces down. So they said 2 times 320 times the sine of 45 equals mass times 9.80. Exactly what we just did for the one we just finished, isn't it? Which is going to be 452.5 divided by 9.8. That gives you 46 kilograms. So therefore, the mass of that object is 46 kilograms. And this time, you'll notice, the angles do have the decimal 0 in them, so they do have 3 sig figs, but the 320 that you see there, 320 newtons, that was only 2 sig figs, so that was the limiting factor. And you can see now what I was talking about with the angles. Normally on the public, they do give them as decimal zeros like that, so that they do tend to have more than 2 sig figs. But the other number here only had 2 sig figs, so that was the limit. Now, let's move on to another one. This one is what you would call a level 3 question again. So, explain using principles of physics which design would best hold a sign. And it's exactly the same idea as what we just did, except we're not given any numbers. So really, the one that would best hold the sign would be the one that has the smallest tension in the cable. Because the greater the tension is, the more likely it is to break. And we don't want the cable to break, because if it does, the sign will fall to the ground. So which one of these would have the least amount of tension, then, is the question. So let's have a go at it and see. So for each of the signs, essentially what we have is tension equals W over 2 sine theta. Let me show you where that comes from. For each of these signs, 2ty is equal to Fg, isn't it? So in other words, 2t sine theta, because that's how we find ty, would equal Fg, which they've got called weight, or W. And that's where that expression came from right here. That's where they got that expression. Okay, and then, moving it on, that means that the diagram, move this up a little bit, the diagram, because A has a larger angle, right? So in other words, this angle right here, which we'll call theta A, is actually bigger than that angle there, which we'll call theta B. And remember, when you're finding the sine of an angle, the smaller the angle is, the smaller the value of sine. Smaller the angle, the smaller the sine. Like the sine of 0, for example. Sine of 0 would be 0, whereas the sine of 10 would be 0.17. The sine of 20 would be 0.34, etc., etc. So as you divide by larger and larger numbers on the bottom, the tension gets smaller. Because the tension here is actually inversely proportional to the sine of the angle. So the larger angles give a larger value of sine, and therefore a smaller tension. So therefore, in diagram A, the angle with the horizontal is larger, and that makes the tension smaller. So diagram A would be the best way to do it. Because the smaller you make that angle, the more strain you're putting on those cables, and the more likely it is to break. So that's why A would be better to hold the sign, because there's less tension in the cables. Same sign, it's just that A has less tension because of what we just said. So hopefully that makes sense to you. One last question before we finish up. This one is pretty similar to ones we've done. This was off a recent public exam as well. We got a 56 kilogram person who has been suspended by cables, and he's just hanging there motionless, which means static equilibrium, no net force. We want to know the magnitude of the tensions in each of these cables. Well, here's the key thing. Here's the key thing right here. Let's have a look. Tension 1 right here, you'll notice that's X only, isn't it? There's no angle here. It's perpendicular. See that? It's perpendicular to this upright. So in other words, this one is actually a horizontal. That's actually an X. So really, we can call that T1X. T3 is the opposite. T3 is straight up and down because the guy is just hanging on to it. So that's actually T3Y. So I've got an X and a Y. And those, like T1, for example, doesn't have a Y component. The Y is 0 for that one. And T3, likewise, doesn't have an X component. So what we do is we need to look to T2. So what I need to do is I need to figure out a T2x, and I need to figure out a T2y. T2x, T2y. And if we can do that, the rest is easy. So let's concentrate on the y's first. T2y is actually equal to T3, okay, which is equal to mass times gravity. Because I don't know what T2 is, I'm going to find T2y first using the fact that T3 is equal to the tension, which is equal to the force of gravity that that guy is hanging with. So putting those numbers in, we get that. T2y equals that, which means T2y, the y part, in other words, of tension 2, is 549 newtons. So that's the first step. Once we figured out that much, now we can say this. Remember that T2y is equal to T sine theta, right? The y component is always T sine theta because the angle is measured from the horizontal. And if you look up here, that angle, 37 degrees, is measured from the horizontal. So coming back down here, you rearrange it and say 549 equals T2 times the sine of 37. That tells you that tension number 2, the tension in cable 2, we now know is 912 newtons. So we found T2. We found T3. The only one left to find now is T1. But remember, T1 and T2x also have to be equal because F net x is 0 as well. Okay, the reason these were equal was because F net y was 0. In other words, the forces up had to equal the forces down, which is exactly what we did there. But the other side of that is that F net x also equals 0. So in other words, we can say that, right? Remember, F net x is also equal to 0. So forces left equal forces right. So tension 1, which was an x, is equal to tension 2, x. In other words, the x component of tension 2. So in other words, T1 equals T2 cosine theta. And the rest is easy. Plugging your numbers. We already know that T2 was 912 because we just calculated that using T3. And now we know that T1 equals 728 newtons. 728 newtons. Now, on the public exam this year, or that year, with the year of this one, if you go back and take a look at the comments that the markers made, the teachers, in other words, who wrote that, and that can be found in the what they call the grading standards. And if you go to that public exam website that I showed you before, they will tell you what some of the common mistakes were. And a lot of the common mistakes here are getting the sine and the cosine mixed up for x and y. That's a very common one. Remember that cosine goes with x, sine goes with y. And it's really easy to remember because alphabetical order, right? X comes before y, cosine comes before sine. So you keep them in alphabetical order, you'll always know which goes with which. Okay, and the other things that people tended to mix up on this one was forgetting to do this, forgetting this step. In other words, finding T2y and assuming that was T2, and then using that up here for T2. But you had to find the actual T2. Remember, T2y is only the y component of the tension. So the actual tension, you have to work it out from that expression right there. And that is static equilibrium, at least one part of it. The other part of it involves rotational forces, which are called torque. And the torque will be the subject of our next lesson, our next topic. So that sums it up for this one. Again, good luck with your studying, and hopefully you'll come back and join us for another session in the days to come.